सर क्लास स्टार्ट होगा।
Okay, good afternoon, everybody. First of all, can anybody tell Sheta to change her username according to the rule and then try to add me here? Please tell Sheta to change the username according to the given rule and then try
अच्छा
to.
सर।
Okay, now it's 4:15. I think we have to start now. So we will start today. We will start series expansion of complex functions. Okay, series expansion of complex functions. The note of this topic has already been given. Uh, the note was written by Prakash sir, who is taking the same complex class in F4, F5, F6 batch. I am following the same note. Okay, I am here saying that I am following the same note written by Prakash sir, but for convenience of teaching, I have just elaborated the note. The content of the note of Prakash sir is same here. I have just elaborated the contents, okay, for this convenience of teaching. Okay. So let's start. First, we know about Taylor's series. Taylor series. Okay. Let okay. Let's start. We know about first we tell about Taylor series. The first topic is Taylor series. Suppose fz is an analytic function within a circle C. Okay, and the center of the circle is the point z equal to z0. See the diagram. There is a circle whose center is at the point z0. There is a circle C whose center is at the point z0, and fz is analytic within the circle. Okay. So if there is a function fz is analytic within a circle C whose center is at the point z0, then the Taylor series expansion of fz is the following infinite series. This infinite series is then the Taylor series expansion of the function fz. So if there is a function fz which is analytic within a circle C having center at the point z0, then the Taylor series expansion of the function fz is the infinite series given in the box. This Taylor series is about the point z0, that is the center of the circle C. So fz is equal to, what is the Taylor series? The Taylor series is fz equal to fz0 plus z minus z0 f dash z0. What is f dash z0? F dash z0 is the first derivative of fz at the point z0. The value of the first derivative of fz at the point z0. Then the third term is z minus z0 whole square. Z minus z0 whole square into f double dash z0 by factorial 2. That is second derivative of fz at the point z0 by factorial 2, and it's going on. Then the nth term of this equation will be, the nth term of this series will be z minus z0 whole to the power n, nth derivative of f at the point z0 by factorial n. and goes on. Since it is a infinite series, so there are infinite number of terms in the series. So in summation form, we can write this as we can write the Taylor's infinite series in the given form. This form, fz equal to summation n runs from 0 to infinity an into z minus z0 whole to the power n, where an equal to nth derivative of f at the point z0 by factorial n. Anybody has any query regarding this? হ্যাঁ বলো. I think it's Nilanjan. Nilanjan, tell me. লোকজন ওয়েট করছে. ওকে. Someone tell Oritro Kundu is not written the username according to the rule. Someone tell him. Okay, now the second topic is now the second topic is convergence of this Taylor series. The convergence of this Taylor series. I am going to this topic. So fz is, suppose fz is not analytic at the point z equal to z1. Suppose there is a point z equal to z1. There is a point z equal to z1 where fz is not analytic. So z equal to z1 is a singular point of fz. Okay. Now we consider that this z equal to z1, this z1 point is the nearest singular point of z0. Okay. Then nearest singular point of z0, and the distance between z0 and z1 equal to r0. Okay. The distance between the point z0 and z1 is r0. Then the above mentioned Taylor series. The above mentioned Taylor series about the point z0. The above mentioned Taylor series is about the point z0. If then this above mentioned Taylor series converges to fz within the circle mod z minus z0 is less than r0. In other words, the Taylor series converges to fz within the circle about the point z equal to z0 and whose radius is the distance from z0 to z1, where z1 is the nearest singular point of z0. Okay, so let me explain it again. Suppose z1 is a singular point of the function fz and it is the nearest singular point from the point nearest singular point of z0, and the distance between z0 and the nearest singular point of it is r0. Okay, z1 is the nearest singular point of fz0. z1 is the nearest singular point of fz, nearest singular point of fz of z0. The nearest singular point of z0 is z1, and the distance between z0 and its nearest singular point is r0. Okay, then the Taylor series about the point z0 will converges to fz within the circle mod z minus z0 is less than r0. Mod z minus z0 is less than r0 is the circle whose center is at the point r0, whose center is at the point z0 and whose radius is r0. That is, it is convergent into the circle within the circle whose center is at the point z0 and whose radius is the distance from z0 to z1. See the picture here, the circle whose center is at the point z0 and whose radius is the distance from Z0 to Z1, that is R0. And what is Z1? Z1 is the nearest singular point of Z0. Okay, now anybody has any problem regarding this? Anybody has any problem? Okay, no problem, I think. So let's go to the next topic. Now we will see by an example the region of convergence of a function fz. Okay, suppose this is a function fz. Fz is 1 by 1 minus z. Okay, then we will see the region where the Taylor series converges. Okay, this is the example of the last topic. Now tell me, the function fz is given by 1 by 1 minus z. Now what is the singular point of this function? Can anybody tell me what is the singular point of this function?
1, sir.
1. Z. Fz equal to 1 by z and z equal to 1 is the singular point. Okay, and it is the only singular point. And we are considering the Taylor series of the function fz about the point z equal to 0. So clearly z equal to 1 is the singular point and it is the nearest singular point since there is no other singular points. So the distance between z equal to 0 and z equal to 1 is 1. So the Taylor series expansion of this function is convergent within the circle mod z minus 0 is less than 1. That is the circle whose center is at the point 0 and whose radius is 1 unit. Any confusion or any question regarding this?
सर सब्यसाची वेट कर रहा है वेटिंग
Huh?
और सब्यसाची इज वेटिंग इन द वेटिंग रूम
Okay, सब्यसाची रियावशाक 4:30 के बाद कोई को भी एडमिट नहीं किया जाएगा. Okay. Now see example 2. Now we are going to example 2. Here fz is given by e to the power z. So fz is e to the power z is the exponential function, and we know that exponential function is analytic everywhere in the complex plane. Therefore, the Taylor series expansion of fz equal to e to the power z is convergent within the whole complex plane. There is no singular point of e to the power z. E to the power z is the exponential function, and exponential functions are always analytic. That is analytic everywhere in the complex plane. So there is no singular point of e to the power z. Therefore, the Taylor series expansion of e to the power z is valid in the whole complex plane. Okay, now we are going to the next topic. Another form of Taylor series. Another form of Taylor series says that the Taylor series at the point z equal to 0 that we have given earlier is fz equal to fz0 plus z0 plus z minus z0 f dash z0 plus z minus z0 whole to the whole square f double dash z0 by factorial 2 and so on. Now in this Taylor series, if we put z minus z0 equal to h, we are putting z minus z0 equal to h, then z equal to z0 plus h. Okay, if we put this thing in this Taylor series, we get that fz0. Here see the uh, series in the box. Fz equal to fz0. In place of z minus z0, we are writing h f dash z0 h square f dash z0 f double dash z0 by factorial 2, and the nth term will be h to the power n, nth derivative of f at the point z0 by factorial n. Okay, this form This form given by H, Z minus Z0 equal to H. By putting Z minus Z0 equal to H in the Taylor series, we get another form of Taylor series. Okay, this form is very important while solving some problems. Therefore, we are giving this form. Now, let's go to Maclaurin series. Maclaurin series is a special type of Taylor series. That is, Maclaurin series can be developed from Taylor series. Okay. Now, what is Taylor series about the point Z0? The Taylor series about the point Z0 is given by, suppose the Taylor series about the point Z0 is given by this equation. This infinite series is the Taylor series about the point Z0. That is Fz equal to Fz0 plus H double F dash Z0 plus H squared F double dash Z0 by factorial 2. That we have learnt earlier. This is the another form of Taylor series about the point Z0, where Z equal to Z0 plus H, right? That is H equal to Z minus Z0. Now, if we put Z0 equal to 0, if we put Z0 equal to 0, then Z equal to 0 plus H, that is Z equal to H. Now, in this Taylor series, we are putting H equal to Z and Z0 equal to 0. Whenever Z0 equal to 0, in this line we have found that whenever Z0 equal to 0, Z equal to H. So, we are replacing in the Taylor series H by Z and Z0 by 0 in the RHS. And by replacing these H by Z and Z0 by 0, we get this form of Taylor series, that is Fz equal to F0. In place of Z0, we are writing F0 0. So F0 plus Z F dash 0. In place of H, we are writing Z, and in place of Z0 we are writing 0. So Z F dash 0 plus Z squared by factorial 2 F double dash 0, and the nth term will be Z to the power n by factorial n, nth derivative of f at the point 0. There is a problem here. This will be 0. This will be 0. Okay. So this form of Taylor series is known as the Maclaurin series, and in summation form we can write this Maclaurin series in this form, that is summation n runs to 0 to infinity an Z to the power n, where an equal to nth derivative of f at the point 0 by factorial n. This form of Taylor series is called Maclaurin series. This series is called Maclaurin series. So Maclaurin series is nothing but a special type of Taylor series. In Taylor series, if we put Z0 equal to 0, then H equal to Z, then we get the Maclaurin series. So by putting Z equal to 0 in the Taylor series, we get Maclaurin series. So Maclaurin series is nothing but a Taylor series about the origin. Whenever we are considering a Taylor series about the origin, then it is the Maclaurin series. The origin, the coordinate of origin, the value of Z at origin is 0. Z equal to 0 is the origin. So whenever we are taking a Taylor series about the origin, we get the Maclaurin series. Now, any question up to this? No question?
सर किसी स्टूडेंट का अभी डिस्कनेक्ट हो गया था, वापस से वेटिंग रूम में है वो.
Shirish,
Yes.
Auditro and Purnoy, they don't have written their user IDs according to the rule. Okay, now it's 4:34. The class has been started 4:05. So I am not admitting anybody. It's not possible to admit. Oh, so it's Nilanjan Dash, I think. Yes. So now going to the example 1. So example 1 says that find the Taylor series of 1 by z about the point z equal to 1 and also determine the region of convergence. The function is given by fz equal to 1 by z. They asked to find the Taylor series about the point z equal to 1 and also they asked to find the region of convergence. Okay. So the function is given by fz equal to 1 by z. We have to expand this fz about the point z equal to 1 in the Taylor series. So the Taylor series expansion of a function fz about the point z0 is given by this. This is the Taylor's infinite series about the point z equal to z0. That is fz equal to fz0 plus z minus z0 f dash z0 plus z minus z0 whole square f double dash z0 by factorial 2 and so on. Okay. Now we have to find the Taylor series about the point z equal to 1. Therefore we put z equal to 1 here. So if we put z equal to 1 in this infinite series, we get this equation 1. This equation 1 is fz equal to f1 plus z minus 1 f dash 1 plus z minus 1 whole square f double dash 1 by factorial 2 and so on. So we have put a z0 equal to 1 in the this will be sorry this there is a mistake here. This will be z0 equal to 1. Z0 equal to 1. This thing will be z0 equal to 1. If we put z0 equal to 1 in this Taylor series about z equal to z0, then we get the Taylor series of a function fz about the point z0 equal to about the point 1 z equal to 1. So here fz equal to f1 plus z minus 1 f dash 1 plus z minus 1 whole square f double dash 1 by factorial 2. Okay. Now, what are the unknown points here? The unknowns are f1. This f1 point is unknown. This f dash 1 is unknown. The f double dash 1 by factorial 2 is unknown. We have to find these functions. Okay. Now, our task is we have to find these functions. So, we know the function fz. We know the function fz here. The fz function is given. The fz function is 1 by z. So, the f1 function is 1. The value of f1 is 1. Now if fz equal to 1 by z, so what is f dash z? That is the first derivative of fz. The first derivative of fz is 1 by z minus 1 by z square. Fz is 1 by z, the value of f1 is 1. The f dash z then minus 1 by z square. So value of f dash 1 is minus 1. F double dash z is equal to 2 by z cube. The value of f double dash 1 is 2. F triple dash z is then minus factorial 3 by z to the power 4. This will be 2 in minus 2 into 3. Since 2 into 3 is the factorial 3, therefore minus factorial 3 by z to the power 4 equal to f triple dash 1 equal to factorial 3 by z to the power 4. Then the value of f triple dash z at the point 1 is minus factorial 3. And so by doing so, if we the nth derivative of z fz will be minus 1 whole to the power n factorial by z to the power n plus 1. By going so, we get the nth derivative of z is minus 1 whole to the power n into factorial n by z to the power n plus 1. And the n value of nth derivative of z at the point 1 will be minus 1 whole to the power n into factorial n. Now putting all these values of f1, f dash 1, f double dash 1, f triple dash 1 and f nth 1 in the equation 1, in this equation, putting all the values of f1, f dash 1, f double dash 1 in this equation, we get the required Taylor series. The required Taylor series is this, that is fz is 1 plus z minus 1 into minus 1 plus z minus 1 whole square into 2 by factorial 2 plus z minus 1 whole cube into minus 3 factorial by 3 factorial plus the nth term will be z minus 1 whole to the power n into n factorial into minus 1 whole to the power n by n factorial. Now, after some algebraic manipulation, we get this form. After some manipulating algebraic manipulation of this uh, series, we get this version of the series. This is fz equal to 1 minus z minus 1. We are just making the minus and plus thing. So z minus 1, this 2 by 2, 2 and 2 factorial 2, these cancel out. So these 2 cancel out. Therefore, we get z minus 1 whole square only. Then these minus 3 factorial by 3 factorial cancel out. So we get minus z minus 1 whole cube and so on. So this is the final form and it is the required result. The required result, that is the required Taylor series about the point z equal to 1. Now if I write it in the summation form, then it took the form fz equal to summation n runs to 0 to infinity the nth term, that is minus 1 whole to the power n into z minus 1 whole to the power n. So this is the required Taylor series. So the first part of the problem has been done. That is, we have found the Taylor series expansion of the function fz equal to 1 by z at the point about the point z equal to 1. Now tell me if anybody has any problem up to this. Now anybody has no problem there? Up to this there is no problem. I am asking again, is there any problem? You can tell me.
No problem.
Sir, so
No
what's the
problem.
meaning of region of convergence?
Region of convergence is the I have already stated this. The region here. I'm going to the first page. The region, the circle. Okay. I have already less than r. The circle z minus z0 is less than r0. That is this circle, in which the function the Taylor series converges to fz. In the part convergence of Taylor series, in the first page, I have said that the Taylor series of a function fz about the point z0 converges to fz within the circle mod z minus z0 is less than r0. That is within the circle whose center is at the point z0 but whose radius is the distance from z0 to z1, where z1 is the nearest singular point of z0. Okay, this circle where the function fz where the Taylor series converges to the function fz is said the region of convergence of the Taylor series. Okay, got it?
Sir, how can I say this convergence? That means that this series comes out to be equal to fz and
1 minute, 1 minute. A train is going beside my house. Okay, now tell me your
sir,
question.
convergence,
Huh?
what does it mean? That the Taylor series is coming equal to the fz. That
Yes,
means
yes, yes,
convergence, or
yes. The
that the
sum
sum
of
till
the
infinity.
the sum of the infinite series, that is the RHS, sum of all the elements of RHS will be, that means convergence.
Oh, sir, sir, but at the beginning, what the box
Mhm,
inside that box, we have defined that fz is equal to this series.
mhm, mhm.
So it is already
Okay,
mean something different.
if before that, before the box, I have already said that if fz is analytic within the circle C, then it is convergent.
Yes,
If fz is not analytic in that circle, then it is not convergent. Now see here, the region of convergence, the nearest. So the region of convergence is chosen so that the singular point is excluded from the region of convergence. Okay. The nearest singular point of Z0 is Z1, and we are mm, region of convergence in such a way that Z0 has been excluded from the region of convergence. That is, in the region of convergence, the function fz must be analytic. In the region of convergence, there is no singular point of fz. All the singular point of fz should be outside of the region of convergence. Okay.
yes,
So you got it?
I got it.
Hello? Am I audible to you guys?
Yes, yes.
Uh,
Anybody please tell me if I am audible to you?
yes, sir.
Okay. Okay, so let me finish the problem here. So we were here, we have just found the Taylor series expansion of the function fz equal to 1 by z at the point fz equal to 1 by z at the point z equal to 1. Now we are we have to find the region of convergence of this function. We have to find the region of convergence. Okay. So test of region of convergence. To find the region of convergence, we will use D'Alembert's ratio test. Okay. Now D'Alembert's ratio test is not a new thing to you. The D'Alembert ratio test has already done in the first semester. Am I right? Can you recall it?
Yes, yes.
Can you recall it? The D'Alembert ratio test. Okay, the D'Alembert ratio test has already done in the first semester. The D'Alembert ratio test says that, what is D'Alembert ratio test? If the nth term is un, if the nth term of an infinite series is un, and n plus 1th term is un plus 1, if the, now see here, if the nth term, D'Alembert ratio test, see here in this box, if the nth term of a infinite series is un and the n plus 1th term is un plus 1, then limit n tends to infinity mod un plus 1 by un equal to L. So the nth term of a infinite series is un, the n plus 1th term is un plus 1, and the limit n tends to infinity mod un plus 1 by un equal to L. Then the series converges if L is less than 1, series is divergent if L is greater than 1, and the test fails if L is equal to 1. So you can recall it. Okay,
You can
now here the resulting series, the series we have found, the series of the Taylor series of the function fz about the point z equal to 1 is this series. That is 1 minus z minus 1 plus 1 whole square. That is the series we have just calculated in the last part of the problem, in the first part of the problem. So the nth term of this series is this term, that is minus 1 whole to the power n, z minus 1 whole to the power n. So un, we are considering the nth term as un. So un is equal to minus 1 to the power n, z minus 1 to the power n, minus 1 whole to the power n into z minus 1 to the power whole to the power n. This is the nth term. So the n plus 1th term will be un plus 1. So un plus 1 is minus 1 whole to the power n plus 1 into z minus 1 whole to the power n plus 1. Okay. So here we have to find the limit. Limit n tends to infinity, un plus 1 by un. So in the reaches limit n tends to infinity, the value of un plus 1, that is minus 1, in the numerator the value of un plus 1, that is minus 1 to the power n plus 1 into z minus 1 to the power n plus 1 by minus 1 to the power n z minus 1 to the power n, the value of un. Now in the numerator, see, in the numerator we are writing, minus 1 to the power n plus 1 as minus 1 to the power n into minus 1, and z minus 1 to the power n plus 1 as z minus 1 to the power n into z minus 1. Then minus 1 to the power n of the numerator and the minus 1 to the power n of the denominator cancel out, and the z minus 1 and z minus 1 cancel out. So we get only limit n tends to infinity minus 1 into z minus 1 mod. So a negative in the mod can be considered as a positive term. So there is no n in this term. So the limit will be minus 1 z minus 1. The limiting value will be this same, this minus 1 to the power into z minus 1 mod. This minus 1 into z minus 1 mod can be written as mod z minus 1. Okay, so the limiting value of un plus 1 by un is mod z minus 1. The value of this limit is mod z minus 1. The limiting value of n tends to infinity un plus 1 un is mod z minus 1. Now according to the D'Alembert's ratio test, the series is convergent is the limiting value is less than 1. So by D'Alembert's ratio test, the series converges if this limiting value, that is mod z minus 1, is less than 1. So this z minus 1 is less than 1 is nothing but the circle, the area within the circle mod z minus 1 equal to 1. That is the area within the circle whose center is at the point 1 and whose radius is 1 unit. Okay, now anybody has problem here?
Yes, sir, we are
Yes,
listening.
sir.
Yes, sir.
So few problems today.
It's totally easy class. Yes.
There should be more problem, I think. Okay, whatever. Now, what we have done in this problem, we have found the Taylor's infinite series of fz equal to 1 by z at the point z equal to about the point z equal to 1, and we have found the region of convergence. The Taylor infinite series of the function fz equal to 1 by z about the point z equal to 1 is this series, and the region of convergence is mod z minus 1 is less than 1. Now it is this process is very lengthy. Okay, there are two parts. In the first part we have to find f1 fz f dash z f double dash z, then we have to find the values f1 f dash to 1 f double dash to 1, then or put all these values in the Taylor's infinite series, then we got the infinite series, then by using D'Alembert's ratio test we get the region of convergence. So it is a very lengthy process. So but there is an alternative method of this problem, of the same problem. Okay, this process is so much is not so much lengthy and is little bit easier, I think. Okay, so let me explain the alternative way to find the Taylor's expansion of a given function, and as well as the convergence of the area of convergence of the Taylor series. Okay, so this is the alternative method, and here we are taking the same function fn if fz equal to 1 by z. So we are asked to find the Taylor series expansion of the function fz equal to 1 by z about the point z equal to 0. Okay, so we have to find the Taylor series about the point z equal to 0. Sorry, z equal to 1. So z equal to 1, these things also imply z minus 1 equal to 0. If we consider this z equal to 1 as a equation, then this equation is equivalent to z minus 1 equal to 0. Okay, so we are writing this because in the function fz, we rewrite the function fz equal to 1 by z in such a way that there should be a z minus 1, this LHS thing, this z minus 1 in the denominator of the given function. Here I have 1 by z. I want to bring a z minus 1 in the denominator of the given function. So I am writing it 1 by z minus 1. Since I am writing z minus 1, to normalize it, I have to take a plus 1. Okay, so this is 1 by z minus 1 plus 1. Why I am writing z minus 1? This z minus 1 is writing here because this z minus 1 is here. We have to find the uh, Taylor series about the point z equal to 1. So z minus 1 equal to 0. Okay, therefore I am taking the z minus 1 in the I am taking the z minus 1 in the denominator of the given function. Okay, so fz has been written in this way: fz equal to 1 by z minus 1 plus 1. So in the next step, we are writing just this thing 1 by z minus 1 plus 1. This thing we are writing at 1 plus z minus 1. That is the unity. We are writing the unity term first. Then we are writing fz equal to 1 plus z minus 1 to the power minus 1. Okay, this 1 by 1 plus z minus 1 thing, we are writing it in the inverse form. That is 1 plus z minus 1 to the power minus 1. Okay, now we are putting u equal to z minus 1. We are putting z minus 1 equal to u. So fz becomes 1 plus u to the power minus 1. So it becomes 1 plus u to the power minus 1. So this 1 plus u to the power 1 plus u whole to the power minus 1, this has a infinite expansion, binomial expansion of infinite series. From binomial expansion of binomial expansion, this has an infinite series. This infinite series is 1 minus u plus u square minus u cube, and the nth term is minus 1 to the power n u to the power n, and where mod u is less than 1. Okay, this series is this 1 plus u to the power minus 1 can be written in this infinite series only when mod u is less than 1. Okay, now in the next step, what we are doing, we are putting again interchanging the value of u by z minus 1. So we are writing 1 minus z minus 1 plus z minus 1 whole square and so on, where mod u is less than 1, therefore mod z minus 1 is less than 1. So in the summation form of this infinite series, we can write it summation n equal to 0 to infinity minus 1 whole to the power n into z minus 1 to the power n when mod z minus 1 is less than 1, and the series converges for mod z minus 1 is less than 1. Okay, so this is the required, these two are the this is the required Taylor series of the function 1 by z at the about the point z equal to 1, and these Taylor series is convergent when mod z minus 1 is less than 1. So this is the alternative method, and I think this method is much more easier than the previous one, right?
Mm, um,
So here is an observation. The region of convergence, the idea of region of convergence will be much clear. See, fz equal to 1 by z, and we have to find the Taylor series about z equal to 1. Now tell me, what is the singular point of fz?
0.
What is the singular point of fz?
Z is equals to 0. So Z is equals to 0.
Can anyone tell me what is the singular point of fz?
So Z is equals to
No,
0.
sir.
Yes.
0.
Zero, zero. Zero.
Z equal to 0. Fz equal to 1 by z. The singular point of fz, the only singular point of fz is z equal to 0. And z equal to 0 is the nearest singular point of z equal to 1. So distance between z equal to 0 and z equal to 1 is 1 minus 0, that is 1 unit. So we have to find the Taylor series about the point z equal to 1. Okay, see the uh, diagram, and z equal to 0, this z equal to 0 is the nearest singular point of z equal to 1, and the distance between z equal to 0 and z equal to 1 is 1 unit. This is the distance, z equal to 0 and z equal to 1, this is the distance, z equal to 0 and this z equal to 1, and this is 1 unit. Okay, and this distance is 1 unit. This is the distance, and distance is 1 unit. Okay, so the Taylor series of fz about the point z equal to 1 is convergent within this circle, is convergent within this circle, that is whose center is at the point z equal to 1 and whose radius is z equal to, whose radius is 1 unit, that is whose radius is equal to the distance between z equal to 1 and the nearest singular point z equal to 0. So any question up to this? Any question up to this?
सर एक बार वापस से बताइए ना, वो रेडियस कैसे निकालें आप?
Huh?
वो रेडियस कैसे निकल रहा है, समझ में नहीं आ रहा.
Radius z equal to z equal to 1 is the point where about which you have to find the Taylor series. So this z equal to 1, and the nearest singular point is z equal to 0, z equal to 0 and z equal to 1. So the distance between z equal to 1 and z equal to 0 is 1 unit. So 1 unit is the radius, right?
Thank you. Yes, sir.
Okay, so today 5-2. Okay, let's 1 hour has been completed, I think. So let's stop the class here for the day for today. Now in from the next day we will learn about what is Lorentz series and find the Lorentz series from a problem, and then we will know about pole and residues, from how to find pole and residues from Lorentz series. Okay, so don't leave anybody. I have to take the screenshot of your attendance.
Sir. अच्छा मारा है.
So I think you don't have any problem regarding
सर एक सेकेंड.
huh?
सर अगर हम लोग का एफ ऑफ जेड है z-5, तो हम लोग का सिंगुलर पॉइंट हुआ 5, तो सर उसका रेडियस कैसे होगा?
फिर से बताओ, मैं सुना नहीं, फिर से बताओ.
सर क्या बोले? ए शांत रहना तुम लोग.
Repeat your question. Repeat your question.
सर अगर एफ ऑफ जेड है z-5.
F of z है z-5. Okay.
हाँ, सिंगुलर पॉइंट हुआ 5.
Z-5
तो सर
नहीं,
इसमें
1 by z-5.
हाँ 1
1
बाई
by z-5, right? Yeah, 1
हाँ
by z minus 5, singular point to a 5. Yes.
तो सर इसका क्या बोल रहे थे, हाँ रेडियस कैसे निकलेगा, रेडियस?
From which point, about which point you have to find the Taylor series.
अच्छा वो पॉइंट देखना पड़ेगा, ठीक है सर हम समझ गए.
If you want to find the Taylor series about z equal to 1, then the radius will be 5 minus 1, 4.
4, yes sir.
Right. Yes.
Okay sir, thank you, समझ गए.
Okay, so any other problem? So no problem at all. So I am leaving the meeting. Okay. So thank you everybody.